In this video, we're going to introduce the concept of probability distributions and expected value. But before we can get to that, I need to define a random variable. Now, a random variable is actually a function, and what this function does, it assigns a number to each simple event in the sample space. So, it's an interesting concept because if you think from algebra, generally, if you had a function like this, f of x equals 3x plus 2, you would actually plug a number into that, and then once you plug the number in, like if you plug the number 1 in, it would actually assign to this the number 5. Or if you plugged a 2 in, it would assign it a number 8. But in our examples, instead of plugging numbers into our function, we're going to plug in simple events like the possible results if you toss a die or flip a coin. So let me show you how this works. So let's start with an experiment. Let's say we toss a pair of 6-sided die. And let's say that we're interested in the sum of the dice. So basically, since I told you I'm interested in the sum of the dice, then we can assign our random variable here, our random variable x, which is our function. It will actually represent the sum of each simple event. So for instance, if I rolled a 1-1 and I plugged that simple event into the function, since I predefined this function to represent the sum, then if I evaluate this function at 1-1, where the first dice is 1 and the second dice is 1, then that would assign a 2 to the random variable. Now if I got a 3-3, then it would assign a 6. So it's just assigning the sum to the random variable. So if I rolled a 4-3, then that would assign a sum of 7, a 6-3, a sum of 9, 3-6, sum of 9, 5-6, sum of 11, 6-6, sum of 12, and so on. So the input values are the possible rolls of the die. So in other words, all the possible rolls. The output values are actually the sums, and actually this is a typo here, shame on me. The sum, because you can't have a sum of 1, so it's really a sum of 2 to 12, not 1 to 12, because you can't actually, right, if you roll 2 die, you can't get a sum of 1, right? So it really should say 2 to 12. And I knew that error was there, and I meant to correct it. Okay, let's look at another experiment. Suppose a pair of cards is selected from a standard 52 card deck. We might be interested in the number of aces selected. And if we let S represent the 52 choose 2 or 1326 possible 2-card selections. Now, since I'm interested in the number of aces, I might let X be the random variable that represents the number of aces that are selected here. So obviously I'm not going to list every simple event here, but let's just talk about a few of them. If I selected the 7 of hearts and the 8 of spades, then if I evaluated that pair of cards at the random variable would be assigned a 0 because there are 0 aces. Remember, X represents the number of aces. And if I got the 2 of hearts, 10 of clubs, same thing. X would be assigned a 0. But let's say I got the ace of diamonds and the 4 of spades. Then X would be assigned 1 for 1 ace. Jack of hearts, ace of diamonds, X would be assigned 1 for 1 ace. And if I got the ace of hearts, ace of clubs, X would be assigned 2. Or if I got the ace of spades and ace of clubs, X would be assigned 2. So the input values are all the possible 2-card selections. And the output values can only be the numbers 0, 1, or 2 for 0 aces or 1 ace or 2 aces. Okay, now let's take a look at this next one here. I think I've corrected this, but let me make sure. Okay, suppose we answer 3 multiple choice questions, and we'll assume each question has 4 possible responses each, A, B, C, and D. Let's say that S is the set of all possible answer sheets submitted. Now, since we could have repetition, that would be 4 times 4 times 4, so 64 possible answer sheets. Let X be the random variable that represents the number of correct responses in a submitted answer sheet. Now, consider these sheets here. AAB, AAA, BAC, BCB, CCA, BCA, and so forth. That would just be a sample of 6 possible answer sheets that I could submit. Now, these are not the same as these down here, but this is just a random sampling of 6. Now, let's suppose the key is BCA. Could someone get 0 correct if they submitted the 3 answers? Yeah, they could miss all 3. They could also get 1 correct, so they could miss 1 problem and get 2 correct, or they could get 2 correct and only miss 1 answer. They could actually get all 3 correct, but there's no way that they could get 4 correct answers. Okay, so really anything greater than 4 wouldn't make any sense since there's only 3 questions. And also think about other numbers like -1 or 2.7. Obviously they wouldn't get, those wouldn't make sense either. So the answer sheet could have 0, 1, 2, or 3 correct answers. So X, the random variable X, could represent the numbers 0, 1, 2, and 3, and then that's the output values. The input values would be all the possible answer sheets you could turn in. Now, I've listed like 6 answer sheets here that you could turn in, and as I said, they're not the same as these up here. But if you turned in the answer sheet ABC, since the key is BCA, you would get none of those correct. Now, if you turned in the answer sheet AAA, then you would have gotten the last one correct, so that would have given you 1 for X. If you do CBA, same thing. You got the last one correct, so you would have gotten 1. BCC, you would have gotten the first 2 correct, so X would be 2. ACA, you would have gotten the last 2 correct, so X would be 2. And then BCA, you would have gotten all 3 correct. So when a simple event is input, the output is the number of correct responses. Okay. Now I could have let X represent the number of incorrect responses or some other representation. So it really just depends on what you wish to observe. I wanted to show you something about that random experiment that we did with the 3 multiple choice questions. So I want you to think, let's see, how many ways could we get none correct? Okay, well that's pretty easy. Since each question has 3 wrong answers, then there's 3 ways to get the first question wrong, 3 ways to get the second question wrong, 3 ways to get the third question wrong. So there's 27 possibilities. Now let me jump all the way over here. How many ways could we get all 3 correct? Well, there's only 1 way to get all 3 correct. Now the 2 in the middle are a little bit tricky, but if you said, okay, how many ways could I get 1 correct? Well, think about it like this. To get 1 correct, you have to either answer only number 1 correct, only number 2 correct, or only number 3 correct. So there's really 3 ways you could get a correct answer, but for each of those ways, there's more than 1 way. So you could get number 1 correct by answering number 2 3 different ways that's wrong, and number 3 3 different ways that's wrong. So let's say that you chose the right answer for number 1. So there's only 1 way to choose the right answer for number 1, right? But then you'd have to have 3 ways to choose the wrong answer for number 2 and 3 ways to choose the wrong answer for number 3. So that's actually 9 ways that you could get number 1 correct. Well, the same thing could be said for number 2. For number 2, you would have to get number 1 wrong, and there's 3 ways to do that. And there's only 1 way to get number 2 correct, and then you could get number 3 wrong, and there's 3 ways to do that. So you take 3 times 1 times 3, that's 9 ways you can get number 2 correct. And similarly, there's 9 ways you can get number 3 correct. Okay, so actually, if you add those up, 9 plus 9 plus 9 is 27 possibilities. Similarly, we could say the same thing for, not exactly the same thing, but we could do this in a similar way. How many ways could you get 2 correct? Well, let's say you got questions 1 and 2 correct. Well, if you get questions 1 and 2 correct, how many ways can you get number 3 wrong? 3 ways, right? Well, what if you got 1 and 3 correct? How many ways could you get number 2 wrong? 3 ways. Or 2 and 3 correct. How many ways could you get number 1 wrong? 3 ways. So there's actually 3 plus 3 plus 3 or 9 ways to get 2 of the answers correct. Now, if you add these up, 27 plus 27 plus 9 plus 1, you get 64. And that's the total number of answer sheets that could be turned in. Okay, now, lastly, I can now determine the probabilities for these values. So the probability that you would get none correct, assuming, now we're assuming you're guessing on all of these, so the probability that you would get none correct, well, since there's 27 ways to get none correct out of 64 possible answer sheets, the probability would be 27 out of 64. And the probability of getting 1 correct, again, there's 27 ways to do that, so that would be, probability for that would be 27 out of 64. The probability of getting 2 correct would be 9 ways out of 64. And as I said before, there's only 1 way to get all 3 correct, so the probability of doing that would be 1 out of 64. And what's interesting, this is actually called a probability distribution. This is actually the probability distribution of the random variable x. And we're going to talk about probability distributions in the next video. But what's interesting, in a probability distribution, when you add up the probabilities for each value of your random variable, it must add up to 1. Because if it don't, either you left out something or you put too much in. So if you add these 4 fractions together, you'll see it does add up to 1. So now we'll extend the concept of probability distributions on the next video.